I'm going to the next topic on the behavior of radon isotopes in the environment. Airborne radon, as you know well, there are variations of indoor radon concentration. Daily variation, seasonal radiation, and entire year variation. See, radon concentration varies with time widely due to many influential factors. Normally, in general, the radon concentration in winter is higher than that in summer. Seasonal variation and correction factors. Indoor domestic radon concentration levels are generally higher in winter than in summer. The increased interior or exterior temperature difference during the heating season, resulting in greater atmospheric pressure differential and enhanced radon ingress via a stack effect. A seasonal correction factor is a multiplying factor applied to a measurement with a duration of 1 or more months in order to derive a meaningful annual average radon activity concentration. The calculation generally assume periodic, annual, typically sinusoidal variation. It is not recommended to use seasonal correction factors derived in other countries as they may not be representative. If you want to use the seasonal correction factors, first of all, you have to correct the data the whole year. Regarding indoor radon, the effect of ventilation on indoor radon levels is significant, as increased ventilation can reduce radon concentration by diluting indoor air with outdoor air and promoting its escape. Here is an example of radon time variation of indoor radon concentration. Here is the radon activity concentration and time of day. Door and windows open, radon concentration decreases rapidly. Then doors and windows are closed, radon concentration increases gradually. Natural ventilation effect is revealed here. Note that the time scale of ventilation is much shorter than the half-life of radon. Equilibrium factor. In an indoor environment, radon progenies can attach to the dust, aerosol particles, walls, or any material found inside a house. As a result, there is no radioactive equilibrium between radon concentration and progenies. We call the equilibrium factor. Typically, equilibrium factor is estimated to be 0.4. There are cases where the equilibrium factor can differ from 0.4 or significantly due to various housing and environmental factors. See? Square. Here, this radon. Triangle. Here, this is equivalent radon concentration. That is radon progeny concentration. Using these two parameters, we can calculate the equilibrium factor. This is a broken line. Equilibrium factor is not stable. Equilibrium factor is negatively correlated with the unattached fraction. As you can see, here is equilibrium factor and unattached fraction. When the aerosol particle concentration is high, the unattached fraction is low, and equilibrium factor is relatively high as more of the radon progeny are attached and stay in the air. I'd like to show you the equilibrium factor in various surveys. 18 cities in Canada, number of dwellings more than 10,000 houses. The technique is graph sampling. In the radon concentration, geometric mean 20 becquerel per cubic meter. The equilibrium factor, the 0.65. Here's the range. 0.2 to 0.82. Ottawa, Canada, 6 by long-term measurement. 51 indoor radon concentrations. Equilibrium factor 0.71. Sweden, 200 houses, 255 houses with short-term measurement. Equilibrium factor 0.44. Pakistan, 138 short-term measurements. Indoor radon concentration 132 becquerel per cubic meter. Equilibrium factor 0.46. Jordan, 21 by long-term measurement. Indoor radon concentration 144 becquerel per cubic meter. 0.4. In Poland, 54 short-term measurements. 300 becquerel per cubic meter for indoor radon concentration. Equilibrium factor 0.32. US, 98 houses with short-term measurements. 260 becquerel per cubic meter for indoor radon concentration. Equilibrium factor 0.25. Czech, 30 houses with short-term measurement. Geometric mean of equilibrium factor of 0.36. In Germany, 136 houses using short-term measurement. 0.34. Here is Italy. 10 short-term measurements, about 200 houses. The equilibrium factor range between 0.34 and 0.48. In Greece, about 50 houses with short-term measurements. Equilibrium factor 0.48 in average. So India, 1,265 houses with most long-term measurement. 63 becquerel per cubic meter for indoor radon concentration, and equilibrium factor is 0.36. In China, 14,593 houses with most short-term measurement. The equilibrium factor 0.48. Regarding outdoor radon, radon in outdoor air generally does not pose a significant health risk to the public population for two main reasons. Radon exhaled from the ground is rapidly diluted to low concentrations in the open air. Typical outdoor radon concentrations range from 1 to 100 becquerel per cubic meter, with an estimated annual average of approximately 10 becquerel per cubic meter. People spend only about 20% of their time outdoors. The radiation dose from outdoor radon exposure is significantly smaller by an order of magnitude than the dose from indoor radon exposure. Due to the low perceived risk, there are no specific regulations or recommendations concerning outdoor radon concentrations, and large-scale measurements have primarily focused on indoor radon. Understanding outdoor radon concentrations is important for radiation protection purposes. It provides a baseline to evaluate the anthropogenic contributions to radon exposure. In regions where outdoor radon concentrations are high or approach indoor levels, outdoor radon could contribute more significantly to the overall radon dose. Outdoor radon levels, along with radon flux, will be utilized as input variables to enhance the calculation of the Geogenic Radon Hazard Index, GRHI, which is one of the approaches used for the designation of radon prior areas. Professor Mehra Can I
Yes.
have
Hello. Yes.
10 minutes break?
Yes, sir. Sure, sir.
Okay. See you after 10 minutes.
Yes, sir. We will resume the lecture after 15 minutes.
Okay.
So, dear participants, so we will resume the lectures after 15 minutes. So, then meanwhile, you can take a break.
Thank you.
Welcome, sir. Professor Tokonami, sir.
Yes.
So we can resume the session if you're okay with it.
Yes, I'm okay. Yeah.
Okay, sir. Then, dear participants,
My talk.
we are resuming this session again.
Yeah. Okay. Can you hear me? Okay. Good. So, donor variation in radon concentrations are primarily influenced by changes in atmospheric mixing near the ground. Night and early morning, a positive temperature gradient develops, leading to atmospheric stratification and reduced mixing. This condition traps radon near the ground, producing the highest outdoor radon concentration. Noon and afternoon, a negative temperature gradient forms, promoting strong atmospheric mixing. This disperses radon more effectively, leading to the lowest concentrations during these times. Here are the seasonal variations of outdoor radon concentrations. Outdoor radon concentrations are highest in winter, higher concentration in winter than in summer. The variation might be independent of meteorological conditions such as temperature, humidity, or a wind, but is strongly influenced by the air mass. This figure exemplified outdoor radon concentrations over 3 years. Vertical variations of outdoor radon concentrations. Here is a sample of outdoor radon concentrations. A vertical gradient in activity concentration and time variations according to a daily cycle are commonly observed. Regarding outdoor radon service, I could summarize these data in this table. United States, 82 locations, ranges 11 to 110 becquerel per cubic meter. Iowa, 111, annual 7 to 55 becquerel per cubic meter. US, Minnesota, 64, 4 to 55 becquerel per cubic meter. Turkey, 4,730 locations. Winter, 19 to 64 becquerel per cubic meter. In summer, 7 to 28 becquerel per cubic meter. Slovenia, 60 locations. Annual measurement, or 1 year measurement, 3.8 to 41 becquerel per cubic meter. China, 165, 3 to 50 becquerel per cubic meter. In Serbia, 56 locations, less than 244 becquerel per cubic meter. Geometric mean 49 becquerel per cubic meter. England, 69 locations. Annual geometric mean is 6 becquerel per cubic meter, which is similar to Japan. Norway, 82 locations. In winter, 4 to 13. Summer, 8 to 210. Lebanon, 24 locations. Summer, geometric mean 19.7, autumn 16.1, winter 13.4. In Ireland, 18 locations, 4.2 to 7.7 becquerel per cubic meter. Japan, 696 locations, 1.8 to 35.3 becquerel per cubic meter. Germany, 173, 3 to 31 becquerel per cubic meter. East Asia, 20 locations for 3 months, 5.3 to 17 becquerel per cubic meter. Spain, 25 locations, 1.2 to 15.8 becquerel per cubic meter. Regarding equilibrium factor, as in the environment, the equilibrium factor outdoors can vary from one place to another and is also influenced by seasonal and temporal changes. In China, 3,348 sites in 19 provinces. Most short-term measurements. Outdoor radon, 10 becquerel per cubic meter. Equilibrium factor is 0.59. Here is the range 0.17 to 0.75. In Germany's 27 stations, long-term measurement. 0.48. Range 0.34 and 0.62. In Tokyo, just one site, but 1 year continuous monitoring. Annual average 0.51 plus minus 0.12. 0.4 to 0.5 for daytime, 0.5 to 0.6 nighttime, 0.45 to 0.5 spring and summer, 0.5 to 0.6 in autumn and winter. In Poland, short-term measurement. Equilibrium factor 0.22. The range 0.06 to 0.33. In Spain, weekly short-term over 1 year, 13 becquerel per cubic meter for radon indoor outdoor radon concentration, the Eating factor is 0.18 plus minus 0.07. One site in New York City in the United States, 7-year continuous monitoring, 4.2 becquerel per cubic meter for outdoor radon concentration, and the Eating factor is 0.67. Soil-borne radon exhalation. Radon exhalation rate is a number of atoms left the unit surface area per unit volume. In other words, we call flux density. Exhalation rate is written by this equation. This is the decay constant of radon. This is emanation coefficient, porosity of the soil, and here is epsilon, porosity of density of the soil and porosity of the soil. Here, this is diffusion length and radium-226 concentration. Emanation coefficient is defined as a ratio between the escaped radon into pore space to the total amount of generated radon. The exhalation process is influenced by many factors, intrinsic factors related to the sample properties itself, extrinsic factors outside medium properties. Here, radon generation by radium decay. This is the geochemical processes. By emanation, radon in soil pore air is present. Radon is dissolved in pore water. And by diffusion, radon are migrated through the soil pores. And by exhalation, influenced by diffusive transport, wind, barometric pressure changes, radon escaped into atmosphere. So by entry, radon enters into the building. Moisture content, it is one of the dominant parameters of radon exhalation rate. Low to moderate water contents. Exhalation increases with water content because increased emanation dominates the process. Saturate point. Beyond a certain water content level, emanation no longer increases significantly. High water contents, diffusion becomes the limiting factor. Radon diffusion through water is much slower than through air, leading to a decrease in exhalation. Here's the moisture content in percent and radon exhalation rate. expressed in millibecquerel per square meter per second. Permeability and porosity in radon acceleration. Permeability and porosity of soil are among the most critical factors of radon concentration due to its short half-life and percentage of radon that escapes from the ground depends partially on its formation depth and the permeability of the soil. Higher radon concentrations are found in soils characterized by higher permeability and porosity because of high radon mobility. The higher permeability, lower permeability. Clay, silt, sandy gravel, and gravel. Radon exhalation from the ground surface affects both indoor and outdoor radon activity concentrations. Therefore, it is important to clarify the exhalation process of radon from the soil to the atmosphere. There are photos of radon exhalation rate measurements. This is a radon in this technique, we measured radon concentration in soil. Here is a passive technique for exhalation rate measurement. Dig a hole and place a passive detector here and cover the lid. Cover the hole with the lid like this. 80 centimeter depth. Waterborne radon. Radon dissolves in water and its solubility increases with decreasing temperature. The concentrations of radon in water may range over several orders of magnitude, generally being highest in well water, intermediate in groundwater, the lowest in surface water. The groundwater is important, being an efficient carrier of radon and possibly a significant secondary source of indoor radon. There is no internationally accepted standards governing the level of radon in drinking water, which are recognized on a worldwide level. Here are recommendations for sampling of radon in water. The sample collection method of water depends on the type and characteristics of the water reservoir. Preventing the leakage of radon is critical during sampling, transportation, and preparation of water samples from sources such as potable water, surface water, or spring water. The sample container should be completely submerged, filled to the top, and sealed without any air bubbles before being removed from the water. here are techniques for radon. Here is the techniques for measurement of radon in water. This is a continuous radon monitor by degassing technique. Here is a liquid scintillation counting technique. Here is a sample and cocktail is here. This is a liquid scintillation cocktail in the vial vessel. The sample is here and cocktail, the upper layer. Three hours after sampling, we can obtain the radioactivity concentration. 15 days after sampling, we can estimate radium-226 activity concentration by taking into account the equilibrium between radium-226 and radon-222. Also, here is a gamma spectrometry. The water sample is filled in the glass vial. We measure the gamma ray emitted from the radon progeny. There are radon concentration studies in air, in water. Bangladesh, 10 samples using AlphaGuard. Radon concentrations in becquerel per cubic meter, 1.4 to 3.2 becquerel per cubic meter. China, 69 samples using Shinji meter, 6 to 127. Finland, 3,000 samples using liquid scintillation counter, 77,000 becquerel per liter. Hungary, using liquid scintillation counter, radon concentration is 100 to 350 becquerel per liter. India, 20 samples using radon 7, 0.5 to 22 becquerel per cubic meter. Iran, 48 samples using the same equipment, radon 7, 4.7 to 31.5 becquerel per liter. Iraq, 20 samples using solid-state nuclear track detectors. This is CR39, 0.36 to 1.5 becquerel per liter. In Germany, 550 samples using gamma spectrometry. Radon concentration ranges 9 to 1,220 becquerel per liter. Malaysia, 27 samples, radon 7, as a detection technique. Radon concentration range from 0.07 to 187. Nigeria, 112 samples, radon 7, as a detecting technique. Radon concentration ranges from 0.95 to 112. Poland, 282 samples using liquid scintillation counter. Radon concentration ranges 0.2 to 1,645 becquerel per liter. Qatar 48 samples using Radon 7, 2.7 to 60.7 becquerel per cubic meter. Saudi Arabia 1025 samples using liquid scintillation counter 0.04 to 67.4. Spain 350 samples, liquid scintillation counter and gamma spectrometry. Radon concentration ranged from 0.224 to 1168 becquerel per cubic meter. In Romania, Transylvania, 1,511 samples using scintillation cell. Radon concentration ranges from 0.05 to 129. Yemen, 19 samples using Radon 7 as detection technique. The radon concentration ranged from 1 to 896 becquerel per liter. In order to reduce the radon in water, we can propose several techniques such as aeration, storage, we keep, hold, and decay, heating and biological process, and granular activated carbon. The choice of the reduction method depends on the factors such as radon concentration in water, treatment cost, system maintenance requirement, and the specific application. Aeration involves spraying or bubbling water with air to release the radon gas into the atmosphere. This is a sample of aeration. Aeration can remove up to 99% of radon from water. Very effective. In granular activated carbon, water passes through a tank filled with granular activated carbon. Radon is trapped in the carbon. The removal efficiency is 70 to 99%. Here's a summary of this topic. Radon levels can vary within the building itself and as well as can fluctuate daily and seasonally. Radon levels can geographically change due to geological features. Radon concentrations are typically lower outdoors due to atmospheric dispersion, but local geological conditions can still cause elevated levels in certain regions. Radon is present in groundwater, especially in areas with high uranium deposits. Radon exhalation is affected by several factors. Now we are going to the next topic on dosimetry of radon isotopes.
Thank you very much, sir.
Yes.
Thank you very much, sir, for your such an informative talk.
Yeah.
So, dear participants, if you have any questions, then you can unmute yourself and ask the question. Dear participants, if you have any question, please unmute yourself and you may ask the question.
Well, good morning, Professor Tokonami. It's Dr. Komal here.
Oh,
Yeah.
nice to meet you again.
Yeah, once again, nice to hear you once again with kind guidance of Professor Rohit. And so, I was listening to your lecture 3 that was on radon measurement, and there were slides on comparison of radon in different countries. When we talk about comparison of radon, that is just a chart, that information, how much concentration in various countries. But suppose we are writing a review paper or something, and we have to give in a comparison data for that. Then different countries have different geological conditions that may have different atmospheric conditions, and many other type sampling may be different. Then how the data of comparison is justified in that case?
Yes, this is a good question, but many researchers use a different type of measurement techniques, so it is not easy to compare, actually. But as I told you in my lecture, there are several international standards on the measurement. In order to keep the reliability, maintain the reliability, I suggest we have to follow the international standard.
Yes, we are following the guidelines of various committees. Yes.
Yeah. So this is my answer. Thank you.
Thank you. Thank you, Doctor.
So there might be one more question from Dr. Mukesh Kumar. He has raised his hand. Hello, Dr. Mukesh Kumar, sir. Are you available there? Dr. Mukesh Kumar, if you have any question, please unmute yourself and you may ask the question. So if any other participant have any question, and you may please ask.
Hello.
Yeah, Bishwajit, you can ask the question.
Hello. Good morning, Professor Tokonami. I have one question we know that some aerosols contaminates radon. So we know the carbons are many effects on environmental effects like warming of global warming and glacier melting of glaciers like that. Is there any harmful effect of radon contamination aerosols on environment?
Yeah. You wrote a question in the chat box, so I understand. To my best knowledge, there's no harmful effect of radon progeny aerosols as a global scale. Actually, from the viewpoint of environmental pollution. But actually, as you know well, radon is the second leading cause of lung cancer this is all.
Yes.
No,
Yes, sir.
not similar to carbon. Quite different. It's okay?
Yes, sir. There is a no, not the that is not majorly affected by radon.
No.
Yes, sir. Okay, sir. Thank you, sir.
Yeah. Thank you.
Dear participants, if you have any other question, you may ask. So, Professor Tokonami sir, I think
Yes.
there are more questions from the participants. So we can conclude this first session of the day here.
Yeah.
And thank you very much for your wonderful talk. And
Thank
we
you.
will resume our the session of next session of this day at 1:30 p.m. Indian Standard Time.
Okay.
So, dear
1 hour and a
participants,
half later.
it's after 1.5 hours.
Yeah. Okay. Yeah.
Yes.
Okay.
So thank you very much, participants, for your patience and active listening during the whole session. So we will meet again at 1:30 p.m. Indian Standard Time at the same same Google Meet link. Thank you very much.
Thank you. See you later. See you again.
Yes, sir. Thank you, sir.